The Maclaurin series for e to the x is that the continuous function f is defined by that function for x not equal to 1. 1 would make the denominator 0. The function f has derivatives of all orders at x equals 1. Write the first four non-zero terms in the general term of the Taylor series for e to the x minus 1 squared about x equals 1. So we're going to take x minus 1 squared and plug it in for all of these x's. And that's what you get when you do that on letter A there. B, use the Taylor series found in part A to write the first four non-zero terms in the general term of the Taylor series for f about x equals 1. So we're going to use that to write this. So we're going to take this that we found in A, and we're going to just minus 1 from it first. So that gets rid of that 1. And here's what you get in B. Then, once we get rid of this 1, once we do this, then we're going to take everything and divide by x minus 1 squared. So when we divide this by x minus 1 squared, that's where we get this 1 right there. And then these powers are going to get reduced by 2. And then there's the general term. Use a ratio test to find the interval of convergence for the Taylor series found in part B. So here is setting up the ratio test. There's 2 extra x minus 1s, and then the factorials cancel like this. We have n plus 1 factorial. Over in the bottom, n plus 1 factorial, but then times n plus 2. So we just end up with n plus 2 in the denominator. But when we take the limit on n, n's only in the denominator, so that'll be 0. And 0 times x minus 1 squared, 0 times anything is 0, and that's always less than 1. So our interval of convergence is negative infinity to infinity. Letter D, let's read it. Letter D, use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. So let's just get rid of this now. If you do f prime, if we take the derivative, that's going to be 0. This will be x minus 1. This will be 2/3 x minus 1 to the third, and so on. So there's the first derivative. And when we plug 1 in, we find out that the first derivative exists. If we're looking for points of inflection happen where the first derivative exists and then the second derivative changes signs. So now if we take the second derivative, we get 1 plus 2 times x minus 1 squared and so on. And what we notice is that all of the values are going to be positive because all of these are to odd powers. So since all of the terms are positive, there's no point of inflection because then there's no chance of the second derivative changing signs. Here is the rubric if you'd like to look at it and see what all the points are assigned to. Function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 is 1, f prime of 1 is negative 1/2, and the nth derivative f at x equals 1 is given by, this is the nth derivative for n greater than or equal to 2. Write the first four non-zero terms in the general term of the Taylor series for f about x equals 1. So if we plug in, we got to start plugging in 2. So they give us the first 2 coefficients right there. So that gives us these 2 right here. Then we start plugging values in for n here to get the rest of the derivatives. There's the next derivative, and then we got to build this. So we're putting this times x minus 1 squared over 2 factorial, excuse me, x minus 1 to the third over 3 factorial, and so on. So here I kind of simplified it. So you get 1 minus 1/2 plus 1 over 2 squared plus 1 over 2 to the third. And we kind of see this pattern. So we have, it's alternating. There's the alternating piece. It's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So there's 2 to the n. And then 0, 1, 2, 3, there's n. And x minus 1 to the 0, 1, 2, 3. So there it is written in sigma notation. B, the Taylor series for f about x equals 1 has a radius of convergence of 2. So Taylor series about 1. So if we're centered at 1, then the radius of the convergence is 2. So this will be 2, and then this will be over here negative 2. So this sentence right here gives me this inequality. Find the interval of convergence, show the work that leads to your answer. So there it is. There's that first sentence, and then we just add 1 to both sides. But now we have to check the endpoints. So here's checking -1. Looks like, when you plug this -2/2, that'll be -1 to the n. But then -1 to the 2n is always positive. So this just diverges by the harmonic series. When we plug in 3, we get 2/2. Those just cancel. And this is the alternating harmonic series. Let's scroll down here. So there's your interval of convergence. It's bad at -1, good at 3. That's letter B. Letter C, the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So we're just going to plug 1.2 in for the first 3 terms. We're going to plug in 1.2 there. So here's what we get. It looks like I simplified a little bit, but in the end, we get 0.905. Letter D, show the approximation found in part C is within 1/1000th of the exact value. So the first omitted term, the remainder of the second degree is the first omitted term, which by, let's say I made that 0.008, the 8's cancel out, multiply top and bottom by 1,000, and you get 1/3000, which is less than 1/1000. Here's the rubric. I'll go a little slower in case you want to pause this. All right, what do we have here? Find the function that represents the series. So this, well, now we're talking about geometric if we're finding a function. If you plug in 0 for this, you get 2 times 1, that's 2. And then the r, what we're multiplying by, I almost said radius, not the radius, what we're multiplying by is x minus 3. So here's a sub 1 over 1 minus r, and did a little simplification. Find the sigma representation of the following function. Well, this is almost a sub 1 over 1 minus r, almost. I got to get this to a 1 by dividing everybody by 4, and then we can make it minus just by going minus minus. So a sub 1 is 3/4, r is -1/4 x, and find the sigma. So I wrote a few out, and then here is the actual sigma notation for that. Find the coefficient of x to the 6th in the Maclaurin series generated by this. So we start with sine of x. So there's sine of x. Replace all the x's with x squared. And it turns out, let's see if I can get rid of this, the coefficient of x to the 6th is -1/3 factorial. That's -1/6. Find the values of x for which the geometric series converges. So here we have a geometric series. R is x minus 5/2. Absolute value of x minus 5/2 is less than 1. Definition of absolute value. Multiply by 2. There's the find the value for which the geometric series converges. There is your radius of convergence, and when you add 5, you get your interval of convergence. Find the radius and interval of convergence of each power series. Let's look at the left. I'll just uncover this. If we look at this one right here, we did the ratio test. Turns out this is what you get when you simplify. Definition of absolute value, multiplying by 3 and adding 2. When we plug -1 into this, we get -1 minus 2, that's -3. So there's where you get -1 over n squared. -1 to the n. There we go. So it's an alternating series. So we did limit as n approaches infinity of 1 over n squared of 0. Converges by alternating series tests. So -1 is good. When you plug in 5, all the way up here, 5 minus 2 is 3. So we get 3 to the n over 3 to the n. That's going to cancel out, leaving that n squared. And p is equal to 2 on this. That's greater than 1, converges by p series. Over here on the right, we do the ratio test. It turns out that all the n's end up in the denominator. So that means you have 0 times x minus 4, but that's going to be 0. That's always less than 1. So the interval of convergence is negative infinity to infinity. I don't think I did. Radius of convergence here is 3, and radius of convergence here is infinity.